Hello, I am Fadi Ghanem, and today I will be telling you about my work implementing arbitrary concurrent writes as specified in CRCW PRAM on general-purpose multi-core processors. Parallel random access machines provides a convenient and powerful parallel computational model to study the algorithmic complexity of parallel algorithms. Many believe that CRCW PRAM algorithms are impossible to support on general-purpose parallel machines due to PRAM's abstraction of the underlying hardware and the lack of support for concurrent memory writes in modern architectures. In the last decade, recent research has disputed the claims of PRAM's infeasibility by introducing new experimental architecture designed around PRAM principles. Furthermore, a research compiler was introduced capable of translating a log-step program for a PRAM algorithm implemented as is into work-sharing structures similar to OpenMP Parallel 4 with comparable performance to hand-optimized code. In this work, I will tell you about a new method to enable efficient implementation of CRCW PRAM concurrent writes on multi-core machines. But first, a quick discussion of the PRAM algorithmic model. PRAM is a shared memory abstraction machine, the parallel analog to random access machines. It makes certain assumptions to abstract the underlying architecture, such as removing limits on memory size or the number of processors available, or assuming uniform memory access to any part of memory, regardless of the location of the originating processor. It also assumes perfect synchrony between all processors. In PRAM, execution is lockstep, and so PRAM statements can be thought of as SIMD instructions of size and elements. In PRAM, an algorithm is described as a series of time steps within which multiple operations are executed concurrently. The PRAM model defines three memory access modes consisting of combinations of exclusive and concurrent reads and writes. Of interest is the concurrent read concurrent write mode, where reads and writes by multiple processors to the same memory cell are completed concurrently. In case of concurrent writes, there are various conflict resolution strategies governing which processor gets to commit its write to a memory cell. These are priority concurrent write. Only the processor with the highest priority can write, the rest will fail. Arbitrary concurrent write. An arbitrary processor succeeds in committing its write, the rest will fail. Common concurrent write. All processors will try to write the same value to the same memory cell concurrently. As it stands, there is no efficient way to implement PRAM concurrent writes as described. There are some attempts in the wild where multiple writes were issued with the expectation that the underlying hardware will resolve the writes, or alternatively use atomic instructions to introduce ordering at the risk of causing serialization problems. To understand where concurrent writes can be useful, let's look at the breadth-first search traversal of this simple 5-node graph. This will be done using a top-down parallel traversal algorithm. For every node we visit, we will assign two values, the parent of the current node and the round when the node was visited. In the first round, we visit the root node. Then in the second round, we visit nodes A, B, and C, and assign the root as their parent. Then on the third round, we attempt to visit node D. However, node D has a problem. It has three different threads, one per parent, all trying to visit D at the same time. And so there are three threads trying to concurrently assign a parent to node D. And depending on which thread succeeds, the value for P will be set accordingly. Now, as far as BFS is concerned, whichever thread wins will produce a valid answer. For this specific case, there are three different traversal trees, all of which are valid. And situations where a concurrent write is used are more common than you think. Here is a list of commonly used parallel algorithms that require concurrent writes. Our solution is based on the fact that for arbitrary concurrent writes, it does not matter who wins among multiple writers to the same memory location as long as one writer succeeds. And so in our solution, we pick the earliest thread to arrive as the winner, while all others will fail and skip the write. To achieve that, we assign an auxiliary memory for every memory target location. This auxiliary is used to determine a winner thread. We also require the round of the current concurrent write step, and we temporarily leverage an atomic compare and swap operation to force an ordering and determine a winner. This algorithm works as follows. Guard the concurrent write with a check on whether an executing thread can perform a concurrent write similar to line 13. At line 6, the set of threads that arrive earliest will check if a winner has been picked. When a winner is picked, the auxiliary memory, in this case last round updated, will have the same value as round as we will see shortly. Since a winner hasn't been picked yet, all threads will succeed at line 6 and attempt the compare and swap at line 7. Only one thread will win, while the rest will fail and consequently fail the check at line 13. The winner will set the auxiliary last round updated to be equal to round and return true and perform the write on line 14. Now, after a winner has been picked, any thread that attempts to check at line 6 will fail and will not attempt the atomic. This will continue until the variable round is incremented at line 16, indicating a new round of concurrent writes has begun. It is worth noting that the maximum number of threads that will be able to concurrently access the atomic at line 7 is limited to the number of processors in the system rather than all possible end writers. This contributes greatly to the speed-ups that we will discuss shortly. Now, we want to check if this solution satisfies our needs. First, it is generic and flexible. It is independent of the algorithm being used. All it needs is an auxiliary memory location per target memory to indicate whether a writer thread has been picked, and a simple counter of concurrent write rounds. This enables this primitive to be used regardless of the algorithm being implemented. Second, it guarantees correctness. This primitive ensures that only one writer is picked per memory location, thus avoiding many problems such as race conditions and undefined incorrect multi-value structures. Finally, it is efficient. It limits the number of threads accessing the atomic operation per node. It also avoids multiple updates to target memory as a result of relying on the underlying hardware, which may result in serialization of writes and many cache coherence updates and invalidates. Now we move on to discussing our experiments. We implemented OpenMP benchmarks for PRAM-based algorithms. For each of these, we implemented 3 different methods for resolving concurrent writes. These are a naive implementation, where we naively issue the concurrent writes while relying on the underlying hardware to resolve ordering. A strict atomic implementation. All n possible writers perform atomic operations to pick a winner, and the winner will perform the write. And finally, our method as described. To measure runtime performance, we ran our experiments on the Andes system at Oak Ridge Leadership Computing Facility. Each Andes node contains 2 16-core x86 processors for a total of 32 processors. The first benchmark we will look at is the linear time maximum algorithm. This is an extreme case of write concurrency where the entire algorithm largely revolves around a very large number of common concurrent writes per memory location. Now, when we compare our runtime to the naive implementation, we notice lower runtime across all problem sizes, with a geometric mean of almost double speed up over the naive approach. We also notice that the strictly atomic implementation is 1.7 slower than the naive approach and almost 3.5 times slower than our method on average. Furthermore, we notice that our method scales well with the number of threads, with a maximum speedup of 1.8 at 32 threads compared to the naive method. Next, we look at the breadth-first search algorithm. For this benchmark, we use the Rodinia benchmark's OpenMP implementation as basis for our comparisons. The original code uses the naive method for handling concurrent writes and was left unmodified. Now, when we compare the runtime of our method to Rodinia's implementation, we notice better performance across all problem sizes with a geometric mean of 2x speedup. Furthermore, we notice that our method has better scalability with the number of threads reaching a maximum speedup of 2.24 compared to native Rodinia implementation. Finally, we look at the Auerbach-Shylock connected components algorithm. For this benchmark, we did not include results for the naive implementation since race conditions caused extensive correctness problems resulting in wrong decisions throughout the run of the benchmark. Now, when we compare our runtime results to the strictly atomic implementation, we noticed lower runtime across all problem sizes with a geometric mean of 4x speedup. Furthermore, we noticed that our method has better scalability with the number of threads reaching a maximum speedup of 4x compared to the strictly atomic implementation. Thank you.